Hello, and welcome to Chapter 4, Section 4.2, which deals with a personal favorite of mine, the unit circle. So unit circle is a very exciting thing. So what are the objectives for this section? We're going to identify what a unit circle is, and we're going to describe its relationship to real numbers. We're going to use a unit circle to evaluate trig functions, and then we're going to talk about domain and period to evaluate sine and cosine functions, and then using a calculator. Okay, so unit circle. So there are different ways to introduce the trig functions, and there's different perspectives. One is using triangles, of course, and one very thorough and interesting one is the unit circle. Okay, so let's consider this unit circle here, x squared plus y squared is equal to 1, where the center is at 0, 0, and it has a radius of 1. If I was to draw it exactly on the xy axis such that the center is at the origin, you could see that I cross the x-axis at 1, 0, because the radius is 1, yeah? So it's going to cross here at 0, 1, here at negative 1, 0, and it's going to cross the y-axis again at 0, negative 1. So let's say I was to measure this circle, okay? Let's say I was to take the real number line and I was just to wrap it around, and I have numbers that correspond to this counterclockwise wrapping, okay? And if I went backwards, it would be negative. And we've already talked a little bit about this in the sense of like going in the positive direction and going to the negative direction, okay? So as the number line wraps around the circle, every number t, any number that you can think of that's real, corresponds to some point xy, right? Because it's on the xy plane, right? So let's say, for example, here, 0 corresponds to 1, 0. Okay, so, but when we think about radians, remember radians, we can also talk about we know that unit circle has a circumference of 2 pi because the radius of the unit circle is 1. So 2 pi r, 2 pi times 1 is just 2 pi. So what we're saying here is, hey, if I was to measure this all the way around, I can say here, this value will be 2 pi, okay? So in general, I can say that every real number t that I find here on the line, like any point that's on this unit circle, I can correspond it to some central angle, right? That vertex is on the origin in the standard position and has a radian measure t. Okay, so what we would say, so let's think about this. The arc length formula that we talked about before, S is equal to R times theta. Okay, so if R is 1, so basically that real number of t is basically the length of the arc that's intercepted by this angle, but it's given in radians. Okay, so it's like an arc length. Okay, so trig function. So let's see here. From before, we know that the x and y coordinates are two functions of t. So we can use those coordinates to define t, okay? So we have here sine, cosecant, cosine, secant, tangent, and cotangent. Sorry, and another, I have to show you guys SOHCAHTOA. That's one way to remember it, and we'll go over that in a second. That's from the triangle way of expressing the trig functions, okay? So, but they're the same thing. They have analogous, they have like analogous counterparts, okay? So I'll show you what I mean. So yeah, so we're talking about sine. So I explained these functions to you. And so here, okay, so we have sine, cosine, tangent. Now, if I have a point on the unit circle corresponding to this value t, right? So we call it, it's in radians, right? We can think of it as a degree almost, right? So since they're equal, right? Or we can think of it as an angle. So sine of that is going to be opposite over hypotenuse. In other words, it's going to be y, and it's going to have this value x for cosine. Tangent is going to be y over x. Then we also have cosecant, secant. These are just the reciprocals of, so cosecant is a reciprocal of sine, secant is the reciprocal of cosine. Okay, so you can think of sine as the y value, and cosine as the x value, and everything else comes from that. So let's see here. So notice that tangent and secant are not defined when x equals 0. That's because x is in the denominator. So let's say, for instance, you have t is pi over 2, right? So we know that that corresponds to the value 0, 1. So then that means that tangent and secant are undefined. Okay, so cotangent and cosecant are also undefined because of the ratios. Okay, so let's go. Let's see here. So let's continue. Going into the unit circle, we can separate them. There's a symmetry about the unit circle, which is really beautiful, and it happens at certain angles. So you can actually take one quadrant, like you can study one quadrant of the unit circle so closely, and this is what people normally do. They memorize quadrant 1, and then they use the fact that there's symmetry to fill in the rest of the circle. So let's say here we divide this into 8 arcs. So we have 0, pi over 4, here's pi over 2, here's 3 pi over 4 pi, 5 pi over 4, 3 pi over 2, 7 pi over 4, and 2 pi. Notice that every point on the circle has corresponding specific coordinates on the unit circle. So like, for instance, when you have pi over 4, x is root 2 over 2, and y is root 2 over 2, okay? And then here, notice that this point here is basically a reflection across the y-axis, right? So the y stayed the same, but the x changed from positive to negative because now it's on the negative side of the x-axis. And so you see how there's like a symmetry here? So from here to here, the x stayed the same, they're negative, but it reflected across the y, so it went from positive to negative on the y. And then finally from here to here, or you can think of it from here to here, it really just depends. You can have, so like if you look at the initial quadrant 1, root 2 over 2 for x and root 2 over 2 for y, looking at quadrant 4, notice that x is still root 2 over 2, but the y is now the negative of root 2 over 2. So you can keep going. So let's say here, so now here's some other famous ones. If you divide it into 12 arcs, you can have 0, pi over 6, 3, pi over 3, pi over 2, 2 pi over 3. So notice that the pi over 6 and 5 pi over 6 are basically reflections of each other across the y-axis, okay? They have the same y value, but the x changed from positive to negative, okay? And there's a lot of symmetry. So if you really take your time to study it and look at it, and you can kind of just learn so much trig, and there's so many values that will be easy for you to access without having to plug it in your calculator and all that. Okay, so let's talk about this. So the unit circle is connected in so many ways. So we know that here root 2 over 2, comma root 2 over 2, this is a point on the unit circle where this lies on the graph x squared plus y squared is equal to 1, right? That's the graph of the circle. That's the equation of the circle. But we know that this is the line y equal x because y is equal to x because they're equal to each other, yeah? So if I substitute it in, x for y, and I solve it, I would get, okay, the 2 points that lie on this, that are on the line y equal x are x is equal to plus or minus root 2. So it's true because here you have positive root 2 over 2, positive root 2 over 2 for x, and positive root 2 over 2 for y. And then down here in the third quadrant, you have negative root 2 over 2 for x and negative root 2 over 2 for y. So that basically that's kind of one way to think about the reflections and stuff like that. And again, I think it's really helpful to imagine it either reflected across the x-axis or the y-axis as well. Okay, so let's see here. So let's use the unit circle. Let's say we want to evaluate the 6 trig functions for just one of these, okay? So let's go into it. So once you have a point on the line, it's very easy to figure out all the other 6 trig functions. So what I would do if I were you, I would write down all the ratios and all the values of sine, cosine, tangent, and the reciprocals And then that's how you would solve the 6 trig functions for just one value of t, or one value of theta, however you want to think about it. So, okay, so let's say here, let's use the unit circle for a. So pi over 6 is where? Pi over 6 is here at x equals root 2 over 2 and y equals 1/2. So remember, sine of pi over 6 will just be the y coordinate, and cosine will be the x coordinate. So, okay, so sine of pi over 6 is y, the y is just 1/2. Cosine pi over 6 is x, so that's root 3 over 2. Tangent is the ratio of y over x. So then if you were to write them on top of each other, you would just get 1 over root 3, but then that would simplify to become root 3 over 2. Root 3 over 3, sorry. And then cosecant, right, it's just the inverse of the sine. So what that means is you take whatever sine of pi over 6 is and then flip it. So 1/2. What's 1/2 flipped over? It's just 2 over 1, so that's 2. And then secant, which is the next one, is the reciprocal of cosine. So that's 2 over root 3, but then if you rationalize the denominator, you would multiply top and bottom by root 3, so you would get 2 root 3 over 3. And then cotangent of pi over 6 is just x over y. In other words, the reciprocal of tangent, and that would be root 3. So then you kind of start seeing how important it is. The unit circle is super helpful because it simplifies our lives. And we can kind of go, okay, well, you need to make sure that you label pi over 6, pi over 3, pi over, you know what I mean? And if you need help with that, there's a lot of cool worksheets and stuff you can download online that deal with the unit circle, and they're super helpful. And if you can't find any, send me a message and I'll make sure that I find something for you to practice. Okay, so let's say t of 5 pi over 4. 5 pi over 4, where is that? That's down here at the, on the, let's see, quadrant 1, 2, 3, right? So that's root 2 over 2. Oh, so this is not the correct picture, but that's okay. So 5 pi over 4 corresponds to the point, it's over here on the 1, 2, 3, quadrant 3, and it's negative root 2 over 2, comma, negative root 2 over 2. So you have x is root 2 over 2 negative, and y is negative root 2 over 2. So you just basically go, okay, since you know sine is y, there it is, cosine is x, there it is. Tangent is the ratio of the two, but they're equal, so that's just 1. Cosecant is the reciprocal of sine, so that's negative root 2, and the secant will be the same thing. And then cotangent, the reciprocal of 1 is just 1. Okay, so then let's say here if we have t is equal to pi. So notice that pi is on the x-axis in the negative direction. So that would be the point negative 1 comma 0. So sine of pi would be 0. Cosine of pi would be negative 1. Tangent would be the ratio y over x, so that would just be 0. The cosecant, it's the ratio of 1 over y, but 1 over 0 is undefined, okay? And so, and then also secant is 1 over x, 1 over negative 1 would just be negative 1, and then cotangent of pi is x over y, which is undefined because of the 0. So, so if we did negative 3, right, negative pi over 3, I mean, if we went clockwise, right, so we would go from here and we went pi over 3, we would get here the point 1/2 negative root 3 over 2. And then from that point, we can find all the 6 trig functions using sine is y, cosine x, tangent is y over x, okay, so you just basically plug in. This is your x and this is a y. So let's restate this in another way. If you're given a t or a theta, okay, on the unit circle, it corresponds to a certain point for a lot of the common functions, a lot of the common angles, right? So let's say here we have, so then we're going to have that point. So we know what's x, we know what's y, and then we're going to use our trig function definition. So we know sine is the y, cosine is x, tangent, and we just basically plug it in, and then you have all 6 functions, 6 trig function values. Okay, so here cosecant would be 1 over y, so that's negative root 2 over root 3. So then when you rationalize this, it's 2 root 3 over 3. secant of negative pi over 3 is 1 over the x values, so the reciprocal of 1/2 is 2. Cotangent is the reciprocal of the tangent, so when you do that, you would get root 3 over 3. Okay, so then let's talk about one more thing, which is the domain and period of sine and cosine. So it's really cool. The domain here, you can see that it goes from -1 to 1, right? And the range is also from -1 to 1. Okay, so that's one thing we can think of, right? The domain is actually, so technically, okay, so the domain is x, right? Sorry, x can be anything. But because the input we're using t, so remember we said we introduced t as the real number. Sorry about that. Let me restate that in a different way. Because we're talking about the domain of the function, not the domain of the circle. Okay, so we're talking about the domain of the circle, but because we defined the sine and cosine functions as sine and cosine of t, but t was the whole entire real number line wrapped around the circle, which just seems kind of crazy, but if you think about it, you can kind of connect. If you were just to count the points, there's infinitely many points possible between two points that are connected by a smooth line that has no holes in it. There's infinitely many possible points. So, I mean, you can say, oh, this is the set of all real numbers, because you can take every single possible little tiny point and correspond it to a point on the number line. Okay, so anyway, so the domain would be all reals, and then the range will just be -1 to 1. Because we defined sine of t is y and cosine of t is x. Okay, so since we saw that on the unit circle, y goes from -1 to 1 and x goes from -1 to 1. So that's this way. Now, I like looking at it graphically, not as a unit circle. When I'm talking about domain and range, it's a lot easier to see. And I'm not sure if I've done that yet, but I will definitely do that if I haven't yet. Okay, so we've talked about this before too, where if you add 2 pi, you find a coterminal angle, okay? You find an angle that does a revolution around the unit circle, okay? So what does that mean? So why do we care about that? Why do we care that it's periodic, that the same value keeps happening if I keep adding, going around? Okay, so let's say I started at 0, but then I travel 2 pi around, I'm still back at the same location here, right? Even though technically I've traveled 2 pi, I'm still back where I started, right? That's what periodic functions do. They keep repeating themselves. Like they'll have this like one turn, right? One period, and then they just start all over again. This is really interesting. Okay, so what does that mean here? So if I take any sine of any number and I add 2 pi to the inside or the input of it, I'm going to get the same value back. Okay, so basically in general, sine of some angle or some t or theta plus, and then 2 pi times an integer n. N could be anything, whether you're adding 2 pi or you're subtracting 2 pi or you're adding 4 pi or 6 pi or whatever. You're going to get back the same value for sine of t. Okay, so that's why, because they repeat and they're cyclic. It's called this is called a periodic function. Okay, so what's a periodic function mean? That means that there exists some number c that when I add it to the input, I get back to the same y. Okay, and then the smallest number for which f is periodic is called the period. So let's say, remember from the past, we know that a function is even when f of negative t is f of t, and it's odd when f of negative t is equal to the negative of f of t. So some trig functions are odd and some trig functions are even. The cosine and secant functions are even because if I plug in a negative t, I get the function back. And if I plug in a negative t to secant, I get the function back. And then odd, sine, cosecant, tangent, and cotangent are all odd functions. Okay, so what does that mean? So let's say here, if we want, to evaluate sine of 13 pi over 6, okay? So basically I'd say, oh, okay, well, 13 pi over 6 is the same as, I can rewrite this as 12 pi over 6 plus pi over 6, or 2 pi plus pi over 6. But because I can like take away a 2 pi basically, I can just find psi of pi over 6 on the unit circle, which is half. Okay, so that's why we had that part of rewriting coterminal angles and learning to subtract and add 2 pi, because we're using it now. So let's say here for negative 7 pi over 2, we know that we could say, okay, well, what if I rewrote this as negative 8 pi plus pi over 2? Well, this negative 8 pi, that's just going, 4 times in the negative direction. So it's actually coterminal to pi over 2. So cosine of pi over 2 is just 0. Okay, so similarly here, would say, okay, for sine of t is equal to 4/5, we know that sine of negative t will be the negative of this because the fact that the sine function is odd. So we use these properties that we're learning about the trig functions to help us like figure out different ones, okay? Okay, so let's use a calculator. Let's talk about calculators. So a lot of calculators don't have cosecant, secant, and cotangent. So what we have to do is we have to either use the x inverse key or we just write 1 over in the calculator, okay? So it just depends. So here's one. So let's say, for instance, you want to do cosecant of pi over 8. You're actually doing 1 over sine of pi over 8. And you can enter this, or you can enter it as, reciprocal, parenthesis, begin parenthesis, sine of, and then within this parentheses here, pi over 8, pi divided by 8, then close it with another parenthesis, and then hit x, this little tiny exponent, negative 1. That means find the inverse of this, and then hit enter, and it'll give you the solution in radians. But you have to make sure that your calculator is in radians mode. Okay, so that's sine of 2 pi over 3, cotangent of 1.5. I would put tan, and then I would hit 1.5, and then I would make sure that I close the parentheses and then hit x to the negative 1 and then enter. Or you could have written 1 over and then in parentheses tan of 1.5, okay? All right, so that's it for 4.2. Your homework is 1 through 45, every other odd, and I will see you guys on the next video.